Flipped classroom video for Further Maths Unit 2, Exponential Distribution. If we have a process where the number of events happening in a time interval of length tau can be modelled by a Poisson distribution with parameter lambda for tau, then the length of time t between the occurrence of consecutive events is a continuous random variable which can be modelled by exponential with distribution with parameter lambda. That is, a Poisson distribution is the number of events that occur in an interval of time, and so is a discrete distribution. The exponential distribution is the time taken between two events, and that is a continuous distribution. We can use the exponential distribution to answer questions like, how long do we need to wait before a customer enters a shop? How long will it be before a call centre receives the next phone call? How long will a piece of machinery work without breaking down? How much time will elapse before an earthquake occurs in a given region? In the Poisson distribution, the mean number of events occurring in an interval of time is lambda. With the exponential function, we have the probability density function given as when x is greater than 0, we've got lambda e to the minus lambda x, and no probability for less than 0. So for various values of lambda, that's what our distribution looks like. Now, if we want a value up to the point x, we need the cumulative distribution of x. We integrate the function up to a point x from 0 up to a point x, so we can use a different variable in the function. So I need to integrate lambda e to the minus lambda t dt. I can take the lambda out, so I'm integrating e to the minus lambda t, so it becomes e to the minus lambda t over the differential of the function, which is minus lambda. I need to put in x and 0. So x is a point somewhere along the x-axis, and I've got 0 in, so e to the 0 would be 1. So I've got a minus here, so I can say, oh, and the lambda cancels with both of them. So this becomes a 1, that becomes a minus e to the lambda x. So my probability up to a point x is 1 minus e to the lambda x. And as x becomes large, this is 1 over a very large number, which becomes 0. So this total probability tends to 0. And we can write this distribution as exponential distribution with a parameter lambda. It's not the mean this time, mind. So up to a point x, we've got that expression. Over a point x, we need to take that away from 1, which leaves us with just e to the minus lambda x. The mean and the variance, so the mean would be integrating x, as it's a continuous function, x times the function. So I've got x times e to the minus lambda x, so there's two values, need to do it by parts. So u would be the x, dv would be the e to the minus lambda x, so uv minus v du, and I put 0 and infinity in. So infinity, if I put infinity in, I've got 1 over a large number, so this is 0. If I put 0 in, the x is 0, so I got 0 there. Integrate again, and I've got the lambda outside, so the lambda cancelled the first time. Now I've got e to the minus lambda x over minus lambda, put infinity in, I got a 0, put 0 in, I've got 1 over lambda, so I got minus, so my mean is just 1 over lambda. My variance, I need e of x squared minus e of x all squared. So e of x squared means I have to multiply the function by x squared and integrate, do that by parts, and so on. Here's one I've done before. So I've got minus plus 2 over lambda squared for e of x squared. So e of x squared minus e of x all squared, and I get 1 over lambda squared for the variance. So the mean is 1 over lambda, the variance is 1 over lambda squared. The exponential function has the key property of being memoryless. That is, if an event has not occurred after 30 seconds, the conditional probability that occurrence will take at least 10 more seconds is equal to the unconditional probability of observing the event 10 seconds after the initial time. So the previous 30 seconds made no difference. We need to time it again. It's memoryless. Each interval is independent. Right, an example. Assume that the length of a phone call in minutes is an exponential random variable x with a parameter lambda is 1/10. If someone arrives at the phone booth just before you arrive, find the probability that you have to wait at least or less than 5 minutes, greater than 10 minutes, and between 5 and 10 minutes, and also compute the expected value and the variance of x. So we want up to 5 minutes, less than 5 minutes, which we use the formula 1 minus e to the minus lambda x. Lambda is 1/10, which is 0.1. X is 5. Work that out. Take away from 1, and I get 0.3935 for less than 5 minutes wait. Greater than 10 minutes would be 1 minus, giving us the e to the minus lambda x for greater than. So I put 0.1 for lambda, 10 for x, and I get 0.3679 for greater than 10 minutes wait. Between 5 and 10 minutes, so I need to work up to 10 minutes and take away up to 5. This is a continuous, so greater than or greater than or less than makes no difference, so I need up to 5. So 1 minus e to the minus 1 minus 0.1 times 10. Take away 1 minus e to the minus 0.1 times 5. The ones cancel, and I have minus minus, so plus e to the minus 1 minus 0.1 times 5 minus e to the minus 0.1 times 10, giving us 0.2387 for between 5 and 10 minutes wait. The expected value was 1 over lambda, so 1 over 1/10 is 10 minutes. We're talking about minutes. And the variance is 1 over 10 squared, which is 100 minutes, was the variance of x. Another example, a checkout counter at the supermarket completes the process according to an exponential distribution with service rate of 6 an hour. Now this is different now. A customer arrives at the checkout counter. Find the probabilities of the following event. It's completed in fewer than 5 minutes, more than 15 minutes after arriving, and then the service is completed between 4 and 8 minutes. So first of all, we need to find lambda. 6 an hour, and we are talking about minutes, so it's 1/10 every minute. Then lambda is 1/10. So our x is exponentially distributed with 1/10, 0.1 again. We want less than 5 minutes, so it's 1 minus e to the minus 0.1 times 5, giving us 0.3935 eventually. B, more than 15 minutes after arriving, so more than is just e to the minus lambda, which is 0.1, and then the 15, and we get 0.2231 for more than 15. Between 5 and 8 minutes, so less than 8 up to the 0.8 minus up to the 0.5 as we continuous. So the two formula in there, the ones cancel, so we've got plus e to the minus, that's 0.5, minus e to the minus 0.8, which becomes 0.1572 for part C. A past paper question from AQA. The lifetime of a high power light is T 1000 hours, where T has exponential distribution with parameter lambda is 0.8. Find the mean value of T, the mean lifetime of a high power bulb, light, and then the probability that a high power light has a lifetime of less than 1000 hours. We'll do that first. So T is exponentially distributed with lambda is 0.8. We want the mean value, so that's 1 over lambda, which is 1 over 0.8, which is 1.25. T is 1000 hours, so the mean lifetime for part 2 is 1250 hours. Part 3, the probability that it has a lifetime of less than 1000 hours, so that makes T's 1, so we want the probability that T is less than 1, so it's 1 minus e to the minus 0.8 times 1, which becomes 0.551. Part B. High power lights are used throughout a large office building. A light has been in use for 500 hours. Find the probability that it lasts for at least another 500 hours. Well, it has no memory, as we said, so we are not considering the previous 500 hours. We need the next 500 hours. So we need T is greater than a half, greater than 0.5, so that's just e to the minus 0.8 times 0.5, which gives us 0.670. Part 3. 3 new lights are installed in one of the offices. Find the probability that at least one of them fails within 500 hours. At least one fails would be 1 minus the probability that all last greater than 500 hours, i.e. none of them fail within the 500 hours. So 1 minus they all last more than 500 hours. Now, we have for lasting, being there's 3 bulbs and we want them to last more than 500 hours, so each bulb has to last more than 500 hours. So we've got my e to the minus 0.8 times 0.5 cubed, as there's 3 bulbs, and then I want that taken away from 1, so I get 0.699 to 3 decimal places. And that's the end of the video on exponential distribution.